Today we want to take a look at vectors and how we can apply them to physics and physics problem solving. When talking about vectors, we want to remember that vectors are fully described by both magnitude and direction. So when we're looking at these vectors, first we want to note that magnitude is noted through the use of scale, and direction is described through the use of angles. So when we look at a vector here, the scale is determined by actually looking at a length. So up here we have that 1 centimeter is equal to 4 meters. So for every 1 centimeter from where we start to where we go out to is 4 centimeters. So if this vector is 5 centimeters long, that 5 centimeters relates to 20 meters. And we can even use a ruler to figure out how long this is. So put that there. Swing that around, and we see that we have 5 centimeters. This is measured in millimeters here, so that's why it says 50. But this is 5 centimeters. 5 times 4 is equal to 20 meters. Also, then we have this 30-degree angle. And we're going to talk about how do we actually denote angles and how do we look at those on an xy coordinate plane. Next, when looking at vectors, we need to determine some terminology about how do we actually talk about vectors and how do we describe them. So first, where a vector starts from is what we call the initial point, or the tail end of the vector. And where the vector ends, or the arrowhead, again this points in the direction of the motion, or the movement, is called the terminal point, or the head of the vector. So we have the initial point where it starts, and the terminal point where it ends. And when measuring angles, there's 3 different scales that we can use to measure out how we actually talk about these angles. One is the counterclockwise angle measure. So whenever we're working with angles, we're always starting on the positive x-axis as our 0 measure here. And what we do is we measure the angle from this point going up to here. So let's say that this is roughly 30 degrees. So this angle would just be measured as 30 degrees. When it comes to another way of measuring the same angle, this is still 30 degrees that's here, but it's 30 degrees away from this eastern direction. It's closest to the eastern direction because we know if this is 30, this here must be 60 degrees. With that understood, we say that this angle here is 30 degrees, and it's 30 degrees away from the eastern direction, but it's to the north of that eastern direction. So we say 30 degrees north of east. Finally, we can write this vector in a separate way. What we do is we first start with either writing the north or the south, depending on which direction it's going. And in this case, this is going up, so we write N for north. Then we determine how far away is this vector from the north, so we look at this angle here. Well, we've already established that each quadrant is 90 degrees, so if this angle down here was 30, this must be 60. So it's north 60 degrees, and then we determine is it going to the east or to the west. And in this case, it's going to the east, so it's north 60 degrees east. So whether we say 30 degrees north of east, or north 60 degrees east, we're talking about the exact same angle. It's just 3 different notations with which to describe it. When we're adding vectors that are at right angles, we can use the Pythagorean theorem to solve for them. So if we have one angle that's going at 10 meters to the east, and then we go an additional 5 meters to the north, we can figure out what this length is equal to by using the Pythagorean theorem. Remember that the Pythagorean theorem states that a squared plus b squared is equal to c squared for any triangle where you have legs of length A and B and a hypotenuse of side C. So in this case, to solve for x, we need to use the Pythagorean theorem. So we can say that 5 meters squared plus 10 meters squared is equal to x squared. So 25 meters squared plus 100 meters squared is equal to x squared. And then we can take the square root of both sides of this. And when we take the square root of 125, we get an angle measure of 11.2 meters for our length of x. Now there are a couple ways we could check to see if this is the right answer. One, we know that the hypotenuse always has to be the longer side. So we can first say, is this longer than both 5 and 10? We know 11.2 is. The other thing that we know is that no side of the triangle can be longer than the other two sides combined. So we say, is this 11.2 less than 5 plus 10, which is 15? And it is, so we know that at least our answers make sense here. After we're done finding the magnitude of a triangle, we also can find out the angle measure. So again, if we have that same triangle where we have 5 meters to the north and we have 10 meters to the east, and we want to find out, and we said we have our 11.2 meters here, what we can do is we can use trig functions to be able to solve this out. Now, when working with trig functions, we're talking about the opposite, adjacent, and hypotenuse sides of the triangle. What we do is we look at what is the angle that we're working from. In this case, we're using the Greek letter theta to denote an unknown angle. From this angle theta here, we know that the side that's opposite is the one that's directly across from here. So our opposite side is going to be our 5. Our adjacent side is the one that's touching the angle here. So our adjacent side is going to be our 10, and our hypotenuse is the one that is across from our 90-degree angle. So that's right there. Now, when working with trig functions, we want to work with the values that were given to us. And in this case, we were given the values of 5 and 10. The reason we don't use 11.2 is we had to round a little bit to get to 11.2, which is going to slightly throw off this answer here. So we want to get as firm of numbers as we can have when we're going forward. So because we're working here with our opposite and our adjacent sides, we know that the tangent of any given angle is equal to the opposite divided by the adjacent sides of the triangle. When we're working with that, again, we see that the opposite and the adjacent sides we're dealing with here, we have 5 meters and 10 meters, so we know that the tangent of our given angle theta is equal to 5 meters divided by 10 meters. To solve for this angle, we need to do the opposite operation. So before, when we multiply with the number, if we had 2x is equal to 18, and we wanted to determine, well, what is x equal to, we divide both sides by 2 to get that x is equal to 9. On the same note, if we had that x squared is equal to 25, we could take the square root of both sides to solve for x to isolate it. When we're working with a trig function, what we can do to bring this tangent away to get this theta by itself is we say theta is equal to, it's something that we call the inverse tangent of 5 meters over 10 meters. And the inverse tangent is just a button. If you have a scientific calculator that has the tangent function, right above there with the second function, we'll have the tangent inverse, or the tangent to the -1 power. You don't need to know how to actually do or calculate these values. All you have to do is plug them into your calculator to solve for the specific value. When we do that, we find out that our theta is equal to a value of 26.6 degrees. Now, we're not completely done here. What we have to do is we have to think back to our xy coordinate plane, where we have our 0, 90, 180, 270, and 360. Now this vector is going up and to the left. It's going into the northwest direction. And we know that this angle, this part of the angle, is the 26.6. But what we want to find out to be able to describe this angle here is, what does this angle measure equal to? So to actually find the direction of the vector that we're working with, we have to do, because it's in this third quadrant, and because we only know this angle measure, 180 minus 26.6 degrees, to get a value of 153.4 degrees for our true direction that we're working with. Finally, the last thing we want to work with on a vector is finding the components of a vector. So let's say we had the opposite forms of information here. Let's say that we knew that we had a vector of 11.2 meters. And with that vector of 11.2 meters, we knew that it had an angle here of 26.6 degrees. I want to find out what are my two components that make up that triangle. So I want to know what is my x component, because it's the one that runs left and right, and what is my y component, the one that runs north and south. To find these two vector components, what I need to do again is I need to go back to my trig functions. So I have SOHCAHTOA, where sine is equal to the opposite over hypotenuse, cosine is equal to adjacent over the hypotenuse, and the tangent is equal to the opposite over the adjacent. In this case, I'm working with my hypotenuse in every scenario because I was given this specific value. Being given this value, I can use that to solve for my y and my x. In the case of my y is across from this angle here, so my y is my opposite side, meaning that I'll use a sine function. In this case here, with this 26.6, the x is the one that's touching this angle, which makes this angle my adjacent side, or this length my adjacent side. So to solve for y, I'm going to say that the sine of 26.6 degrees is equal to my opposite side, which is side y, divided by 11.2 meters. Now to solve for y, I have y divided by something is equal to something else. So to move this over, I need to multiply both sides by 11.2. And when I do that, I get that y is equal to 11.2 meters times sine of 26.6 degrees. And when I work that out, I get that y is equal to 5.01 meters. Now you may be asking yourself, well, when we did the problem before, why did we get that this was equal to 5 meters? We knew that it was 5 meters, and we had 10 meters down here. Well, why is this 5.01? This comes as a product from the rounding that we did earlier. Again, whenever we're talking about the numbers that we're given, we look at the values that were initially provided to us, because our other values will have some rounding that takes place. On the same note, when we find out my x value, because it's the adjacent side, we say that cosine of 26.6 degrees is equal to x divided by 11.2 meters. X is equal to 11.2 meters times the cosine of 26.6 degrees. So x in this case is equal to 10.01 meters. And by finding these components, we can actually find a lot about how do we add vectors together, how do we use that addition to determine the true motion of a given object.